This is your presenter Asloob Mudassar, and I am presenting slide number 134 of the course on laser physics. Question is, what is passive mode locking? Give the types of important passive mode locking techniques. Discuss at least 3 important passive mode locking techniques in detail. The answer is, in passive mode locking, a non-linear optical element is inserted into a laser cavity which is not driven by any external voltage source and which, due to its non-linear effect, induces the process of mode locking. Four main types of passive mode locking are fast saturable absorber mode locking, Kerr lens mode locking, slow saturable absorber mode locking, additive pulse mode locking. And we shall present these four techniques one by one. In fast saturable absorber based mode locking, the absorber must satisfy two properties. Number A, it should have a low saturation intensity. B, it should have a relaxation time much shorter than the duration of the mode locking pulses. That is, so let me say again, it should have low saturation intensity, which means that even the absorber becomes saturated at low values of intensities. And the second condition is that it should have a relaxation time much shorter than the duration of the mode locked pulses. So relaxation time mean that if the absorber is at one time in a saturation condition, then it becomes unsaturated spontaneously without any delay. However, we discussed the fast saturable absorber mode locking for homogeneously broadened gain medium. So you see that we are going to discuss this technique, that is the fast saturable absorber technique for a homogeneously broadened gain medium. Let us represent the absorber's saturation intensity by IS. So IS is the intensity at which the absorber becomes saturated. That is, it becomes almost transparent. And with saturation mean that the loss due to the absorber becomes minimum. And the intracavity beam intensity by I. So I is the intensity of the laser within the cavity, and IS is the saturation, is the intensity at which the absorber becomes saturated. Cavity round trip power loss can be written as. So the loss equation, the power loss equation can be written as given in equation number 1, that is 2 gamma T is equal to 2 gamma minus 2 gamma prime times I over IS. Again, this I is the intensity of the laser beam. This IS is the intensity at which the absorber becomes saturated. And 2 gamma T, the 2, you see that there is a factor of 2 with each one because these are the losses for one round trip of the cavity. That's why we have multiplied by 2. And individually, these are the losses for a single pass. So I am going to explain this equation first and then we shall move ahead. Where gamma is the unsaturable single pass loss. That is when the absorber is unsaturated, the loss due to that one is gamma. And gamma prime is the single pass loss of the saturable intensity under the condition that I is much smaller than IS. So under the condition we have this loss, that is gamma prime. And so gamma prime is the single pass loss of the saturable intensity under the condition. So you see that under this condition, that is when the intensity of the laser beam is non-zero, we have a single pass loss that is given by gamma. From this equation you can see that if the intensity of the laser, which is I, is 0, then of course this term will vanish out, and 2 gamma t will be determined only by the factor 2 gamma. But if the intensity I is non-zero, then of course this 2 gamma prime will come into play, and then this 2 gamma t will be determined by the difference of 2 gamma and 2 gamma prime times I over Is. Let us consider that a laser is initially oscillating with the mode phases unlocked, and a rate and that a very thin absorber is placed in contact with one of the cavity mirrors as shown in part A of figure number 132.4, that is in slide number 132 and equation number 4, with shutter replaced by a thin absorber. So let me show you this figure in the appendix, where we have replaced the shutter by a thin absorber. In part A. So you see that here this is a shutter which is very close to mirror M2, and for our present case we are going to replace this shutter with the thin absorber. So our fast absorber is placed over here. The rest of the things will remain the same. This is active medium, and we are going to place our absorber very close to one of the cavity mirrors, and here we have placed it close to mirror number 2. And the length of the cavity is represented by capital L. And this is the pulse. You see that the pulse has been shown, which is incident on the shutter, but in our present case the pulse will be incident on the absorber. So let us consider that a laser is initially oscillating with mode pulses unlocked, and that a very thin absorber is placed in contact with one of the cavity mirrors. So you see that we are imposing that the condition, not a condition, but a situation that that an intensity that initially the oscillating, that the laser is initially oscillating with the mode phases unlocked. So let me show you what is the meaning of the intensity of the laser when the phases are unlocked in an appendix 1. For example, this one. And you see that this is the figure we have taken from the slide number 132 and figure 1. So this is the output from the laser beam. And you can see that the laser spikes over here. These are the laser spikes. And you know that this is the period tau p, because after the tau p the pulse are being repeated. And this is the output from the laser, which is unmode locked laser. And you know that we want to, for example, this is the peak which is high, which has the highest intensity, and we can select this intensity, for example, because we shall assume that the losses for these smaller peaks is higher, and we can select that peak which has the highest intensity, so that it can oscillate within the laser cavity, and ultimately it will come out from the laser cavity as a mode locked laser. Because when this is presented to the absorber, when this peak is presented to the absorber, all the other peaks except this peak and this peak, which have the same intensity, for example, will be retained. The rest of the pulses will vanish out because these will be blocked by the absorber. Because according to the saturation of the absorber will allow the intensities which have the higher peaks. And for example, we want this peak to be transmitted through the absorber. So once this peak is transmitted, the other peaks will not be transmitted, because we shall make the arrangement in such a way that the other peaks will be absorbed by the system, and only this peak will be propagating between the laser cavity. And of course the mode locked pulses will be based on one of these spikes which we choose as our oscillating spikes. But you know that if we choose any spike which has a lower intensity, then of course the other higher spikes will automatically be selected. So if you select the highest peak spike, then of course the rest of them will be automatically blocked. And this is what we have taken from again slide number 132 and figure number 1. So here this is what we have said. Let us consider a laser is that a laser is initially oscillating with the mode pulses unlocked, and the figure I have shown you just in appendix 1, and that a very thin absorber is placed in contact with one of the cavity mirrors. This is also I have shown you in appendix number 2. The modes oscillate with an intensity of the form shown in figure 132.1. This is the figure that I have shown you in appendix number 1. For low peak intensity, the saturated round trip power gain, which is represented by 2g naught prime. So this you see that this is the round trip power gain. The saturated round trip power gain 2g naught prime is roughly equal to the cavity unsaturated loss. The most intense peak will have the least saturation due to saturation of the absorber. This pulse will then grow faster in comparison with other peaks, and eventually the situation is shown in figure 130 in figure number 1. So let me show you figure number 1. This is figure number 1. The caption of the figure is mode locked pulses achieved in a passive mode locking by a fast saturable absorber. Along the vertical axis, we are plotting three quantities: 2 gamma t, g naught prime, and I, where I is the intensity of the intensity within the intracavity intensity, that is the intensity within the laser. G naught prime is the gain of the active medium, and 2 gamma t is the net loss. And you see that we have plotted the two quantities are constant. One is 2 g naught prime. You see that this is the horizontal line, solid line, which is constant with the time. So the gain of the system is constant with the time. And you see that I have shown also a horizontal line parallel to the g naught prime line. This is the unsaturated loss 2 gamma. So you can see that the unsaturated loss 2 gamma is constant. Unsaturated loss means that is the absorber is in the unsaturated condition, then the loss is higher. So when the absorber is in the unsaturated condition, it will present highest possible loss, which is this one shown in the dotted line and is a horizontal line. And you see that there is another quantity which is called the saturated loss 2 gamma t. And you know that 2 gamma t was obtained in the expression from equation number 1. Let me show you 2 gamma t. And 2 gamma t is actually the difference between 2 gamma and 2 gamma prime times I over is. You see that we have to compare our net loss, which is 2 gamma prime. 2 gamma t, sorry, 2 gamma t. We have to compare 2 gamma t with the net gain of the system, which is 2 g naught prime. So when the net gain, you see that the net gain has been, the net loss has been presented, which we call the saturated loss 2 gamma t. So 2 gamma t is the loss under the saturated condition. That is when the absorber under the saturated condition means that this dip in the curve correspond to the condition when the absorber gets saturated. Here, this part of the curve is the curve when the absorber is again unsaturated. And you see that it is very close to the unsaturated loss 2 gamma. But when the absorber gets saturated, you will see that a dip occurs in the loss, and the loss becomes smaller than the active medium gain of the active medium. So when the loss becomes, when the absorber becomes saturated, the loss it presents becomes smaller. And when the loss becomes smaller than the gain of the active medium, then of course you will see that a pulse will grow. That is, a pulse will appear in the time t1 and t2. So T1 and T2 is the time between which the absorber will be saturated, and after that the absorber before and after that the absorber will remain unsaturated. The absorber being unsaturated means that it will present the maximum possible loss in the cavity, and when the loss is higher the output will be zero, so no light will be, no intensity over here, no laser intensity is over in this region. So again you see that this pulse will repeat after a time tau p, which is the time after one round trip. So this after one round trip again you see that this will be presented to the absorber, and then it will be presented to the absorber, and again this pulse will be transmitted, because the absorber is when it suffers, when it encounters a very high intensity, the absorber gets saturated. So due to a very high intensity the absorber gets saturated, and of course the loss it presents become smaller than the gain of the medium, and so you can see that the peak can pass through the absorber, and so this process will continue, and this peak will again and again will be presented to the absorber, and once this pulse has passed through the absorber, the relaxation time of the absorber is so short that the absorber becomes unsaturated, and the other data, the other peaks which were present in the profile of the laser will be stopped by the saturable absorber, that is will be absorbed, will be saturated, will be absorbed, so will be stopped by the absorber, because then that when the absorber is not in the saturation condition it will present the maximum loss to the oscillating laser pulses. So only this pulse will be transmitted, because here we are assuming that this pulse is the highest pulse. No, so all the pulses which are below this value, they will not pass through the absorber, because the absorber will present a maximum loss to them, and they will appear like this one, because in this region the absorber is in the unsaturated condition, presenting a maximum loss. So outside the region from T1 to T2, where the absorber is in the saturated condition, presenting minimum loss, the pulse will appear, but at the other regions where the intensity of the laser is zero, it means that the saturable absorber, that is the absorber is in the unsaturated condition, presenting maximum loss, and then that loss will be, you see that is higher than the gain of the medium. For example, you can see this solid line over here, and when the loss is very high, you see that the laser output will be zero, and only the laser output will appear when the loss becomes minimum, and this only happens at the saturation condition of the absorber. So the once this pulse will pass through the absorber, the relaxation time of the saturable absorber is so short that it will immediately come in the state of unsaturation, and under that condition no pulse will pass. So let me show you again through the appendix, when the unmodulated signal, unmode locked laser is presented to the absorber, then of course you see that one of the peak, for example, the peak with the highest intensity, for example, will be selected. The rest of the peaks will be stopped, because the absorber will be in the unsaturated condition for the rest of the peaks except the peak which has the highest intensity, and this will pass through the absorber, because the absorber will be in the saturated condition due to this peak. This peak will saturate the absorber because the intensity is higher. For the higher intensity, the absorber will be in the saturation condition, presenting the minimum loss to the peak, and under that condition the net gain becomes larger than the net gain of the due to the dip in the loss of the curve. The net gain becomes larger. You see that 2g naught prime becomes larger than the net loss in this region. So we can say that from T1 to T2 we have a window of net gain. So I have explained the working of the mode locked condition. So this pulse, which is the mode locked condition, will now oscillate and will reappear at a time T1 to T2. and will be presented to the absorber, because the absorber will now be in the saturated condition whenever this will come to the absorber, because this intensity is automatically is so high that it will set the absorber in the saturated condition very immediately, because the response of the absorber is very quick. So under that condition, this peak will pass. It might be possible a trailing edge of this peak might be lost initially when the first time the peak passes through the absorber. So you see that each time the peak will get narrowed, because the edges, this edge, small edge, for example, this front edge, when will be presented to the absorber, it will try to switch the absorber to the saturation condition. So a small edge of this one might be lost during each time the peak will be presented to the absorber. So the peak gets narrowed. But at the same time, when this peak passes through the active medium, gain medium or the active medium, then the active medium make this profile slightly broader. So the absorber makes each time the peaks is slightly smaller, whereas the active medium rod, whereas the active medium gain medium makes the pulse slightly broader. So these two things will compensate each other and a steady state operation will be obtained. And so the laser pulses in the form of mode locked pulses, which will appear as an outcome from the laser. So you see that now I am just going through these paragraphs, because from the figure I have explained everything. That is the working of the saturation. That is the working of the absorber has been explained. But I want to just go through these paragraphs, these texts in the paragraphs. So let us consider that a laser is initially oscillating with the mode pulses unlocked, and that a very thin absorber is placed in contact with one of the cavity mirrors, which I have shown you in appendix number 2, the figure 132.4 reproduced there. The initially that the laser was unmode locked was presented in appendix number 1. So this figure 132.1 was reproduced in appendix number 1. So a very thin absorber is placed in contact with one of the cavity mirrors. The modes oscillate with an intensity of the form shown in figure this, because initially the modes are unlocked. For low peak intensity, the saturated round trip power gain, which is the 2 G naught prime, is roughly equal to the cavity unsaturated loss. The most intense peak, you see that here we are talking about most intense peak. The most intense peak will have the least attenuation due to the saturation of the absorber. This pulse will then grow faster in comparison with other peaks, and eventually the situation shown in figure number 1 is established. So you see that this is the figure 1, which I have explained in very detail, and I have also explained how these pulses will be formed as a mode locked pulses, and why the rest of the pulses will not be oscillating. The round trip saturated loss 2 gamma t becomes smaller than the round trip saturated gain, which is 2 g naught prime between the times t1 and t2, and thus a net gain is established in this interval for the pulse, where the pulse tails undergo a net loss. You see that each time the pulses pass through the absorber, a slight cut down of the tails of the pulses will happen, because these pulse will enter and will try to switch the absorber to its saturation condition. So some of the intensities will be lost, and the pulses will narrow down each time when they pass through the saturated absorber. A pulse shortening thus occurs each time the pulse passes through the absorber, and of course the absorber should be in the saturation condition. The pulse shortening, however, is compensated by the finite gain bandwidth of the active medium. The active medium will try to broaden these pulses slightly. The two processes compensate to ensure steady state pulse operation or pulse oscillations. the amplitude of the steady state pulse, because the steady state condition has been established now and the pulses are now oscillating back and forth within the laser cavity. The amplitude of the steady state pulse can be described by a hyperbolic secant function, that is so E as a function of time is the amplitude of the steady state pulses, that is amplitude of these pulses, these laser pulses. That is the amplitude of these laser pulses has been defined by the secant hyperbolic function, and the argument of the function is T over tau p, where tau p is the pulse repetition time. So here you can see that tau p is the pulse repetition time, because once this pulse this pulse will pass, the other pulse after completing one round trip of the cavity will again be presented to the absorber. So this is the repetition. So repetition will occur by the time tau p. So you see that if you want to find out the amplitude of these pulses, the amplitude is given by this expression as given in equation number 2. The duration of the pulses delta tau p, that is the line width of this pulse delta tau p at full width half maximum is given by. So you see that is delta tau p is actually the width of these pulses. The width of these pulses at half width from the peak. So we can say that it is the full width half maximum of the peaks represented by delta p, and delta tau p is then given by, for the above conditions, that 0.79 divided by delta nu naught multiplied by g naught prime over gamma prime and multiplied by the square root of is over ip, where is is the saturation intensity at which the absorber gets saturated and ip is the intensity of the peak pulse. So the intensity of these peak pulses is ip. And delta nu naught is the full width half maximum gain bandwidth. So delta nu naught is the gain bandwidth of the system, and IP is the intensity of the peak pulse. The medium gain should be long enough to show constant behavior during the passage of the pulse. So you see that our gain medium should have a should be long enough to show constant behavior during the passage of the pulse. You know that I have plotted the gain of the medium, which is 2g naught prime, which is constant with time. So it is a very long process, so it remains constant, you know. The medium gain should be long enough to show constant behavior during the passage of the pulse. It is required that is in the formula, in this formula, because is is given by this one, which is the saturation intensity is given by h nu over 2 times sigma tau for a two-level system, should be small. As tau is small, in this expression the value of tau is small. So which means that the absorption cross section sigma should be very large. So tau is very small. So if tau is small, then is should becomes larger. But you know that sigma becomes larger over here. So the absorption cross section sigma is larger. So that makes is quantity is to be effectively a small quantity. Cyanine dye for mode locking has an upper state relaxation time of a few tenths of a picosecond. So you can notice that the response time is much faster for this cyanine dye of the order of a picosecond, for which the absorber remains saturated. So our absorber remains saturated for a few tenths of a picosecond, and after that it becomes unsaturated. So when it is in the saturated condition and in the time between T1 and T2 as in the previous figure, so during that time the absorber being saturated presents very minimum loss to the oscillating pulses. Mode locked pulses shorter than a few picosecond cannot be obtained through this process. because we have to use a dye and the response of this dye is of the order of a few tenths of a picosecond. We cannot obtain pulses shorter than this one. A semiconductor material, however, with a multi-component decay and a multi-quantum well material between the two mirrors have also been used as a saturable absorber with relatively shorter times for the pulses. So we have completed a description of one technique, and that was a fast saturable absorber technique. Passive technique based on fast saturable absorber. This is what the first technique we have completed and one of the most common technique. Now we are going to present the next passive mode locking technique based on Kerr cell. The next we describe the passive mode locking based on Kerr cell. So first, before I read these paragraphs, let me give you an idea so that while reading the paragraphs, you can have a full understanding what I am talking about. You see that equation number 4, that is the refractive index of the Kerr medium is a function of the intensity. That is, that is the refractive index becomes a function of the intensity. Refractive index remains no more constant for the Kerr lens. So if you are using a Gaussian profile, for example, and you know that in the Gaussian profile, the intensity is maximum in the center, whereas it decays in the form of a bell-shaped form on both sides of that maximum intensity. And if the similarly, if you have intensity in the form of a Gaussian profile, then the refracting index will also attain the shape of a bell-shaped Gaussian profile. That is, the refracting index could be maximum in the center or minimum towards the edges. So we actually modify through the intensity the refractive index of the material within the Kerr cell, and the Kerr cell now becomes the Kerr lens. That is, you know that in the lens you have a thickness in the center, and then of course that thickness while you go away from the center of the lens, the thickness of the lens decreases in a convex lens which is used to focus the beam. Similarly, the same thing happens over here. Actually, you are creating a lens from the which we call a Kerr lens by modifying the intensity, by modifying the refractive index of the material within the Kerr lens by the incident intensity, because the intensity shape, or because the intensity of the incident beam has a Gaussian shape, so the refractive index of the Kerr lens will also attain the Gaussian shape, so it will becomes it will work as a spherical lens, as a spherical convex lens, which we shall call a Kerr lens, and it will focus the laser beam. And when the intensity is not, and when the intensity is small, then of course the refractive index or the refractive index will not be stronger, and of course the focal length of the Kerr lens will not be enough to focus the beam, and the beam will remain diverged. This is what we are expanding the refractive index. For example, the refractive index, you know that is given by this expression. We can expand this refractive index using some polynomial. For example, Taylor series can be used. The first two terms have been retained in the expansion. So the refractive index n is equal to n naught plus n2 times I, where I is the intensity, which I have talked to you that usually we use the Gaussian beam as the intensity. So you see, we have we can this term, that is the second term in the expansion by the Taylor series. This second expansion n2 times I can be regarded as a delta n. That is the change in the refractive index is equal to n times into I. and the Gaussian intensity that we shall be using in order to generate the current lens will be equal to this one, that is I is equal to IP into e to the power minus r square divided by the square of w over square root of 2, where r is 0 in the center of the beam, and r gets its value as you move away from the center, and w over square root of 2 is the beam spot of the Gaussian beam. And if you want to know the further details, you should consult my one of the previous slides about the Gaussian beams. And then we have this is the spot size of the Gaussian beam, and IP is the peak intensity in the center of the beam. You know that when you set R is equal to 0, then you will have I is equal to IP. So IP is the peak value when R is equal to 0, that is in the center of the Gaussian beam. So this is the Gaussian profile that we use on the Kerr cell to make it a Kerr lens. So the phase through the lens material, through the Kerr lens or through the Kerr material will change like this one. That is the change in the phase of the material will be equal to delta phi will be equal to delta n times KL. So this is what you see that by definition of the phase we have written refractive index, change in the refractive index multiplied by K multiplied by L, where L is the length of the medium of the Kerr cell, and the delta phi is the change which is encountered by the light when it passes through the Kerr cell. And you know that if you look at my one of the previous slides on Fourier optics, where I have discussed the convex lens, there you can see that we write down the phase factor of the lens as e to the power minus iota k over 2f into x square plus y square. So you see that this has a very similar form, delta phi. So you need to put delta phi in the form of e to the power iota k over 2f, similarly to the form of the lens there. So I would suggest that if you want to see the details that how the spherical lens focuses the beam incident on that one, you need to consult my some slides on the Fourier optics relevant to the spherical lenses. So let me show you see the Kerr effect. So you see that this is the beam, this is the power input from the cavity of the laser beam. This is incident on the Kerr medium. Now this beam is of the Gaussian shape. So this becomes when this beam will pass through the Kerr medium, it behaves like a Kerr cell. That is the Kerr lens. When it becomes a Kerr lens, it will focus the beam because it becomes a spherical lens. So it will focus the beam, and when the beam will focus, I have shown a larger size of the aperture, but in effect the aperture is very narrow. So this Kerr lens will focus the input beam, and because this Kerr lens is placed in the laser cavity, it will focus the beam at the output aperture, and so the light will come out from the aperture. So this will form an output beam. But you know that when the intensity is not enough, this Kerr cell will behave like an ordinary cell. And then you see that the beam is as shown in the dotted line after the Kerr cell is diverged out and will not pass through the aperture, and so will not contribute as an output beam. So the Kerr cell which automatically works is actually a self-focusing of a high power beam. Only high power beam, because we designed the Kerr cell only for a high power beam. The other beams which have the lower intensities will not will diverge out. Actually, will leave the cavity. Only high power oscillations will sustain within the cavity due to because only high power pulses will make the lens will make the Kerr lens to act as a spherical lens, and of course the light will then be after that will be focused on the output aperture and will come out as an output power beam. So the caption is self-focusing of a high power beam due to intensity dependent non-linearity of the Kerr medium, because the Kerr medium has a non-linearity which depends upon the intensity of the beam. So you see that this is the cursor. Now I am going through quickly the paragraphs so that you can quickly understand, because I have given you a review. Now I am very quickly going through these paragraphs. So writing in equation number 4, writing a refractive index as a function of intensity. This phenomenon is known as optical Curry effect, and on atomic scale it is due to the hyperpolarizability in the medium which occurs at high electric fields. The electric field causes the deformation of atomic or molecular electronic orbitals in solids and reorientation of elongated molecules in gases or liquids. It is very rapid with a response time of a few femtoseconds. You, you can notice the response of the Kerr material having a response of the order of a few femtoseconds. First term in the expansion of the Taylor series given by. So from equation number 4 can be expanded using the Taylor series as this: n is equal to n naught plus n2 times I, where I is the intensity of the input beam. Here we are assuming that I is very powerful beam, so I is very high because the input power incident on the Kerr cell is very high, where n2 is a positive coefficient with a typical value of the order of 10 to the power minus 16 centimeter square per watt. We consider a Gaussian beam, so I should be in the form of a Gaussian beam. Now we consider a Gaussian beam having a high intensity in the center, which decays non-linearly and vanishes at the wings. That is, vanishes at the edge of the beam. The beam will induce a non-linear refractive index delta n, which corresponds to the second term in equation number 5 as delta n is equal to n2 times I, because in equation number 5 only the second term, which we have separated out over here as in the form of delta n is equal to n2 I, will only change due to this one. So the second term has been written because it is intensity dependent and it will change due to the powerful intensity incident on the Kerr medium, which is positive in the center and approaches to zero in the beam wings, because this will follow the same profile as the profile of the Gaussian beam. For a pulse with the IP is the peak intensity. So if a pulse is coming with a peak intensity, having a peak intensity value IP as the peak value and W as the field spot or the size of the spot of the laser beam, the intensity of the pulse is given by. So this is the incident laser intensity having a Gaussian profile, and this should be incident on the Kerr medium. The beam, while traversing a length L of the medium, where L is the length of the Kerr medium, will acquire a non-linear phase shift delta phi, and delta phi is equal to delta n times k into L. Equation number 6 and equation number from equation number 7, from equation number 6 and equation number 7, delta n has a Gaussian dependence, and to a first order it has a dependence of the order of R over W square. For example, it is also evident from the profile that you can see that it has a dependence of R over W square. So similarly, this dependence will be reflected in the refractive index of the medium. So from equation number 6 and 7, delta n has a Gaussian dependence, and to a first order in R over W square, delta phi acquires the profile of a parabolic function of R over W. Because you know that a Gaussian profile more or less is also parabolic at its wings, that is away from its peak value. Due to this, a spherical lens effect is induced in the optical material called Kerr effect. So you can notice that Kerr effect is the effect which is actually the effect when the spherical lens is induced in the optical material due to the intensity distribution incident on the Kerr cell. A beam with the optical power exceeding a critical value. So you see that a critical value is required. So over the intensity of our Gaussian input beam, which is incident on the Kerr cell, should have a critical value. So that is IP, the peak value intensity of the peaks must have a critical value. So a beam with optical power exceeding a critical value may be focused due to Kerr lens, and the phenomenon is known as self-focusing. When a Kerr medium is placed in a laser cavity, as shown in figure number 2. So let me show you again this figure. We have the Kerr medium and an input intensity powerful beam is incident in the form of a Gaussian beam on the Kerr medium, and then the self-focusing occurs at the Kerr lens because the Kerr medium now acts as a Kerr lens, and of course it will focus the beam at the output aperture. This aperture is very small, and then of course output beam will be obtained and the output pulses will be obtained. So a beam with optical power exceeding a critical value may be focused due to Kerr lens, and the phenomenon is known as self-focusing. When a Kerr medium is placed in a cavity, for example figure number 2, then a higher beam intensities, then at higher beam intensities, the beam is focused at the aperture center and is transmitted. The cavity loss may be considered minimum in this case. For pulses with reduced intensity, the Kerr medium does not act as Kerr lens, and the beam is not focused at the aperture and so not transmitted. The mode locking operation can thus be achieved with a Kerr lens which has a very short response time, provided the input intensity incident on the Kerr cell has exceeded the critical value. So you see that now we have completed the description on the Kerr lens as a mode locking device. Now the third scheme that we are going to discuss is the slow saturable absorber mode locking. Okay, next we describe the slow saturable absorber mode locking. The mode locking under slow saturable absorber is implemented if some conditions are fulfilled. You see that we are going to first give you the conditions. What are the conditions? Relaxation time of the absorber should be of the order of 2L over C. And you know that 2L over C is nothing but the cavity round trip time. So over slow saturable absorber should have a relaxation time of the order of 2L over C. Relaxation time of the gain medium should also be of the order of 2L over C. That is both the absorber and the gain medium, that is the active medium, should have the same same time relaxation time, and the relaxation time of the order of 2L over C equal to cavity round trip time. The saturation fluence of the gain medium, which we call as gamma Sg. So this is the saturation. Gamma stand for the fluence, S stand for saturation, G stand for gain. So gamma Sg is actually the saturation fluence of the gain medium, which is given by 2h nu over 2 sigma g. This is what we have also discussed in one of our previous slides. So you can also consult my previous slides on this topic. That is the fluence or the saturation fluence is given by this expression. The saturation fluence of the gain medium, which is gamma Sg, is lower than the intracavity laser fluence. And intracavity laser fluence means that the laser which is propagating must have, so this gamma Sg should be smaller than gamma intra, where gamma intra corresponds to the intracavity laser fluence. And you know that fluence is nothing. What is fluence? Fluence is actually the energy incident per unit area in a given period of time. For example, between time t1 and t2, the energy incident on the material per unit area between time t1 and t2 will be referred to as fluence. The saturation fluence of the saturable absorber, which is gamma SA, is equal to h nu over 2 sigma A. You see that this gamma SA is the saturation fluence of the saturable absorber, SA. SA as a subscript stands for saturable absorber, and gamma stands as the fluence. So fluence of the saturable absorber is given by h nu over 2 sigma A. So here we have the sigma G when we're talking about the saturation fluence of the gain medium, and when we are talking about the saturation fluence of the saturable absorber, we have sigma A. So this gamma Sg and this gamma Sa both must be smaller than the intracavity fluence, and this gamma Sa should be smaller than gamma Sg. So gamma Sa is lower than the intracavity laser fluence. So this is the relation we have written. That is gamma intracavity should be greater than the gamma Sg, and gamma Sg should be greater than gamma Sa. That is the fluence of the saturable absorber should be smaller than the fluence of the saturable fluence of the gain medium, which should be smaller than the saturable which should be smaller than the fluence of the intracavity fluence. So this condition, so you see that here we have listed down some conditions that are required for the slow saturable absorber mode locking to work. So let me explain this figure first, because everything is based on this figure. Once this figure has been explained, then of course then the paragraphs that I shall go through will be will be easier for you to understand. The caption of the figure is temporal behavior of obtaining mode locked pulses using a slow saturable absorber. You see that we have shown the pulses within the time t1 and t2, and again within the time t1 and t2, and we have shown tau p as the pulse repetition time, because this pulse repetition time is now equal to the cavity roundabout time, which is 2L over C. So these pulses will repeat after this time. So that's why I have used the same time t1 and t2 for these two pulses. So these are the mode locked pulses. Initially, the beam will be incident as an unmode locked laser. So I am plotting three quantities over here: gamma, which is the saturable loss, G, which is the saturable gain, and I, which is the intensity of the pulses. So initially you look at the dotted curve. The dotted curve is the saturable loss, gamma. And now look at the saturable gain, G, through a solid line. This solid line represents the saturable gain, G. Now, window of net gain. Look at the window between T1 and T2. The gain curve has now gone, the saturable loss gain now has fallen below the value of the gain in the time T1 and T2, where the value of the net gain is higher than the losses. So a net gain is produced. So the gain is higher than the losses, and a net gain is produced. Due to that net gain, the pulse will pass through the medium between time t1 and t2. So after the pulse will pass through, what will happen? The medium becomes unsaturated. So no other pulses will pass through in this region. You can notice there, because the losses now are higher than the gain of the medium. So output is 0 in this region. Again, you see that after some time, which is equal to the round trip time, which is equal to the round trip time of the cavity, which is equal to 2L over C, where capital L is the length of the cavity. You can see that now the saturable gain loss, the saturable loss falls below the value of the gain, and the gain becomes greater than the loss. So the net gain is higher. So the net gain is generated, and due to net gain, the pulse will grow in this region. So you see that again. Okay, so this you see that this is the scheme. So these pulses, you see that when they will repeatedly pass through this material, which is the saturable material, what will happen? These pulses will narrow down, but you know that the active medium rod will make these pulses, that is the gain of the medium will make these pulses slightly broader, and of course these two things will compensate each other, generating steady state pulses. So this is, you see that the behavior is very close to the previous fast saturable absorber, but you know that the curves are different in that case from this present case. So now giving you just a little bit idea about how the things will work. Let me go through the text. So this is what I have talking. I have previously talked about the fluence of the gain medium, the fluence of the saturable absorber, and the fluence of the intracavity. And this relationship must be obeyed. And the second is that the relaxation time of the absorber and the relaxation time of the gain medium should be much higher. And you know that when the relaxation time of the absorber is there, and when the absorber is saturated, what happens is that when the pulse comes in, it becomes saturated. That is, when the pulse comes in, the absorber in this window, the absorber becomes saturated, and due to that one, the gain of the absorber falls below the gain of the medium. And then you know when the pulse has passed, again it becomes unsaturated, and you see that it again gets a very higher loss in comparison with the gain of the medium. Let us assume that the absorber and the gain medium are located close to one of the cavity mirror. The situation is the same as I have shown over here. Instead of this shutter, we are placing our slow saturable absorber close to one of the cavity mirrors. And this active medium, I think, is also to be placed very close to that one. So both, that is the active medium and this absorber, shutter replaced by an absorber. So the slow absorber and this active medium should be very close to each other in this condition for this technique to work. So let us assume that the absorber and the gain medium are located close to one of the cavity mirrors. Initially assume that the gain is smaller than the losses. The foot of the leading edge of the pulse suffers a net loss. So this is the leading edge, over. This edge is leading. So this will suffer a net loss because it will initiate the process. The foot of the leading edge of the pulse suffers a net loss. We assume that the pulse has such total energy fluence that the accumulated energy fluence of the pulse becomes comparable to the saturation fluence of the absorber during the leading edge of the pulse. So the pulse of our energy fluence of the pulse at its foot even becomes greater than the saturation fluence of the absorber during the leading pulse of the pulse. The absorber starts saturating during the pulse leading edge presented at a time t1, and the absorber loss becomes equal to the laser gain. So when the pulse is presented, so this leading edge when presented at a time t1, Some loss will occur because the light is entering to the absorber and the absorber starts saturating very quickly, and allowing when it starts saturating very quickly, the loss due to the absorber falls below the value of the gain in this region, and then of course this pulse is transmitted because there is a net gain, and due to that net gain the pulse will pass through. So just at a time t1, you can see here in this region the net loss and the net gain are equal to each other. But as you pass through beyond the value of time t1, the net loss, the loss becomes smaller than the gain. So net gain is generated and the pulse is magnified there, or the pulse can pass through in the region. The absorber starts saturating during the pulse leading edge at T1, and the absorber loss becomes equal to the laser gain. Beyond T1, Beyond T1, the pulse then sees a net gain. During the process, the gain medium is required to get saturated, so that during the process, that is between T1 and T2, during the process, the gain medium is required to get saturated, so that during the trailing edge at T2, the saturated gain becomes equal to the saturated loss. And beyond T2, the pulse sees a net loss. So again at time t2, you can see that the net gain and the net loss are equal to each other, and after that one the saturable gain becomes larger than, because it is in the loss due to the absorber becomes larger than the gain. So no output in this region. And when it will repeat after time tau p, then of course the same situation will appear between time t1 and t2. So thus a window in time between T1 and T2 of the net gain is formed. So this is the window where the net gain is generated. A steady state condition for the pulse is reached when the pulse shortening by the absorber is balanced by the pulse broadening due to the finite gain bandwidth of the gain medium. So this is what we have also discussed, the shortening and the broadening and the generation of the steady state pulses when we were talking about the fast saturable absorber technique. So this figure explains the mode locking process using a slow saturable absorber. So this figure gives you the temporal behavior of obtaining mode locked pulses using slow saturable absorber. Now the third technique, the third technique that we are going, this is the fourth technique, because we have presented the three techniques. Now this is the fourth technique. So let's talk about a little bit about it. A few words about the additive pulse mode locking technique. In additive pulse mode locking, two cavities of equal lengths up to accuracy of wavelengths are used. So you see that here we are talking about the use of two cavities of equal length, and the length of the cavity should be very accurate to within the wavelength, or to within the wavelength, or between, or due, or accuracy should be should be a fraction, should be to a precision of the fraction of the wavelength. In one of the cavities, a suitable nonlinear optical element is inserted called auxiliary cavity. So in one of the cavity, we insert a suitable nonlinear optical element, because all the passive techniques work on the generation of non-linear optical elements. Main pulse in the laser cavity and the pulse from the auxiliary cavity are made to interfere. So you see that we have the two pulses, one is the pulse from the laser cavity, the other pulse from the auxiliary cavity, which contains the nonlinear material. The output from these two are made to interfere. The pulse from the auxiliary cavity is phase modulated by the nonlinear optical element. Due to the interference, pulse shortening mechanism occurs and the mode locked pulses are produced. The technique requires two cavities to be equal in length with accuracy equal to a fraction of wavelength of light, which is undesirable and difficult to implement. The technique is therefore not attractive and further detail will not be given. So you see that we have presented three techniques in much greater detail, and just for the fourth technique, we have just given you a flavor that how this fourth technique would work. So this is the end of slide number 134.